Let's talk about inverse trigonometric functions. So 13.4. How do you evaluate inverse trig functions and then solve trig equations? So we're going to kind of talk about two different things. You're going to want a couple handouts with you. So the handouts that I have online look like this. So one of them is trig functions, and basically it's the graphs of all the trig functions. I don't actually expect you to know these this year, but you do need to be familiar with them. And then the second one is inverse trig functions. So these are the inverse functions of the previous page. All right, so these are your two handouts that you need. All right, so I'm going to start right in with something that you already know how to do from last year. So we're going to solve sine of theta equals 1/2. Okay, so what this is saying when it says to solve is you have to basically get the variable by itself. In this case, the variable is theta. That's the thing that we don't know. And what this is saying is that we have the sine of some angle that's 1/2, but we don't know what that angle is. Okay, so this is actually means the sine of what angle equals 1/2. So that's the question that we have to answer. And there's a couple ways to do this, and I'm going to show you both ways. The first way that I'm going to show you is basically we have to get theta by itself. Now, sine always has to have an input. So your trig functions, sine is not an individual thing. Sine of some angle is the individual thing. So you can't just divide both sides by sine to get theta by itself. Trig functions don't work that way. Okay, they always have to have an input with them. So instead, what I'm trying to do is I'm trying to undo the sine function. And as we learned a few chapters ago, the way that you undo functions is by using the inverse. Because if I use the inverse of sine to undo sine, I'll just be left with the input. But I'd have to do that to both sides. Okay, so we're going to use the function's inverse to undo the function. So that's what you need to do. Use the function's inverse to undo, that's the key, the function. You can't just divide. Okay? All right, so that's what you're going to have to do anytime you got to get theta out of a trig function, or anytime you got to get the variable outside of a trig function. Or basically what that means is to solve the function. Okay, so in order to do this then, I do the inverse on both sides. So I'm going to do sine inverse of sine of theta, okay, which basically these two now undo each other. I'm just left with theta, equals sine inverse of 1/2. So you're left then with theta equals sine inverse of 1/2. And of course, one way to do this is to get on your calculator. It didn't tell me whether this was going to be in degrees or in radians, but I'll go ahead and I'll make sure that I'm in degrees for now, so that the answer can kind of make a little bit of sense, because otherwise if it gives us radians, it's probably going to be a decimal that won't look familiar to us. All right, so to do sine inverse, you do secant sine, gives you sine inverse. I'll put 0.5. Okay, so notice what I'm getting here. I'm getting theta equals 30 degrees. Okay, so this should look familiar to you in a couple of ways. One second, let me find my unit circle. So look through your unit circle. So first of all, 30 degrees was the angle of which the sine is 1/2. Well, remember on your unit circle, right, you have your 30-degree angle here, of which the sine is 1/2. So maybe another way to have done this is to know your unit circle and to say, well, the sine of what angle equals 1/2? Well, the sine of 30 degrees would give me 1/2. So sometimes it's that easy. Or if it was like radians, it would be pi over 6. Sometimes it's just that easy. You don't even have to get on your calculator. So knowing this unit circle can help you solve some of these trig functions trig equations quite easily. Okay. Let's talk about example 1. Now, there's going to be several parts to this, and I'm going to have to introduce you to some new stuff, okay? Evaluate. Notice how I'm not saying solve, okay? We're going to evaluate the expression in both radians and degrees. Okay, so first one we'll do is sine inverse of root 2 over 2. So the question then, and I can rewrite this, this is basically going to equal some angle, right? Because the sine of some angle is going to give you this root 2 over 2 coordinate. So it might be nice to set this equal to theta, and then do the opposite of taking the inverse of both sides. Basically, take the sine of both sides, right? Because if I take the sine of its inverse, I'm going to be left with the output again. Or sorry, with the input, not the output. Okay, so what I could do here is I could say to myself, let me take the sine now of both sides. Now these two undo each other, right? If you take the function and you put the inverse function inside of it, they undo and you just are left with the input. So this might be one way to look at this. So now you can ask yourself, sine of what angle would equal root 2 over 2? And again, this is a unit circle issue. This should look very familiar to you. Root 2 over 2. On your unit circle, every 45-degree angle, or pi over 4, right? It's over here as well. Root 2 over 2. We got root 2 over 2's. I mean, there's positives and negatives, and you have to think about that separately. Now, this happens to be a positive one, root 2 over 2. So I know that this is going to be a 45-degree angle. Okay, so I know, and it says radians and degrees, so I know then that theta, or right here, I could have just gone right here and said this is 45 degrees, or pi over 4 radians. Okay, but I know that theta here is going to be either 45 degrees or pi over 4 radians. Okay, so now you might be asking yourself, well, how did I know that I was going to use pi over 4, or the 45 degrees, instead of the 135 degrees, or the 3 pi over 4? Because those both have outputs of root 2 over 2 for sine, right? Sine is your y coordinate. Okay. How did I know it was this one and not this one? Okay, so let's take a little break here. Well, it's not a break. Let's go ahead and let's look at our trigonometric functions. Okay, and you're going to want a highlighter as well. I'm going to do a little bit of highlighting for you. So let's look at our sine function, which is the very first one. So this is, and there's a lot of information on here. Don't worry about all of this right now. But this is y equals sine of x. Notice the domain right now, right? It continues. It goes forever in the x direction both ways, positive or negative. The range, however, the highest point it goes to is 1. Okay, so that's positive 1. And the lowest point it goes to is negative 1. So the range right now, okay, the only outputs we have are negative 1 to positive 1. And everything in between. Okay, don't worry about this right now. Alright, so now turn it over. Nope. For you guys, you might turn it over. I printed it on 2 separate sheets of paper. Now let's look at the graph of sine inverse. So the sine inverse graph is your first one right here. also remember that when we talk about inverse trig functions, it could also be arc sine. Okay, so instead of sine inverse, it could be the arc. Okay. Now, when we take this graph, and inverse functions are always reflected over that line y equals x. So basically what that means is we take every single point and we switch x and y. Hopefully this is ringing a bell for you, bringing back some memories. Then we get this inverse graph of sine. Now the problem with this inverse graph is that this is not a function. Remember, functions pass the vertical line test. This function is not passing the vertical line test. So what we have to do is we have to restrict our domain and our range on our parent graph, or this original trig function, in order to make our inverse trig graph an actual function. And we call this the parent branch, principal branch, not parent branch, sorry, the principal branch. So I'm going to highlight for you the principal branch. And we can look at it from just down here. So the range is restricted for the inverse graph. In the original function, in this original graph then, the domain is the problem. The domain is what we're restricting. Remember how we switch x and y? So that means that domain and range get switched, just like x and y, when you go from the original graph to the inverse graph. So instead of having this domain in the original graph go from negative infinity to positive infinity, in which case in the inverse graph, this would just continue to go along that y-axis forever. Instead, what we do is we restrict that domain, which now at this point, it's the range, and it goes from negative pi over 2 to pi over 2. So I'm going to highlight from negative pi over 2 up to pi over 2. Okay, so that is the principal branch. Let me go ahead and this part is the principal branch. Ooh, which principal? I feel like that's the way you're supposed to spell it. Let's see if I have any other notes on that. Ooh, it might be pal. Principal. I think it's principal branch. That's how I have it spelled. And I feel like I've done this before a million times. Every year. Okay, and then notice that the domain, so this is important stuff down here, the domain for sine inverse goes from negative 1 to positive 1. Well, guess what? Originally, in the original function, the range went from negative 1 up to positive 1. So now we go from negative 1 over to positive 1 along the x-axis because everything's been switched. Okay, so Miss Frisk, wow, you really went into that, didn't you? I sure did. Now, the reason I'm telling you that is because you're asking me, why am I using a 45? How do I know it's 45 degrees and not, let's go back to this, and right, the 45 degrees had that positive root 2 over 2, and not 135 degrees. Well, the reason I know that it's going to be the 45 degrees or the pi over 4 and not the 135 degrees or the 3 pi over 4 is because of this principal branch. I am only allowed to go from negative pi over 2 to pi over 2. I'm only allowed to use these angles. Pi over 4 fits in here. It's half of pi over 2. So looking at it like using my unit circle or my quadrants, I could say that for the sine inverse or even for the sine function when I'm trying to solve for an angle. Okay, but so basically that's using sine inverse. I'm allowed to go from negative pi over 2 to pi over 2. That's where my angles can fall. Okay, so I'm just allowed basically quadrant 1 and quadrant 4. I can find angles in those two quadrants. Okay. Okay, so now let's go back. Let's apply this then. Oh no, that was sine as well. Those are both sines. Okay, cool. So actually I will apply it to this one too because in my previous example, I said I was looking for the angle that gave me an output of 1/2. Well, how many angles are on here that give me an output of 1/2? 2 of them, right? 30 degrees and 150 degrees. But which one am I allowed to use? Again, I'm stuck in the sine inverse. If I use sine inverse, I'm only allowed to go in the first quadrant or the fourth quadrant. So that's why I chose that 30-degree angle and not 150 degrees. Also, my calculator gave it to me. So it's important that you're thinking about all of this stuff as we move forward. Okay, let's see another example. We'll keep coming back to these papers, so have those with you. And I think we'll do B now, so we can talk about cosine inverse as well. Okay, so for B, I know, or here's the problem, cosine inverse of 3, that's what I need to evaluate. And then remember, evaluate is actually like find an answer for it. So the question here is cosine of what angle would give me an output of 3? So I'm going to put like a little thing here. Think about taking the cosine of both sides. So the question is, the cosine of what angle will give me 3? Now right away a little alert should go off in your head. Because when we were talking about these functions, and I haven't actually showed you the cosine function yet, so let's talk about that right now. The cosine function, the original cosine function with no transformations or anything, looks like this. It starts on the y-axis, so its y-intercept is 0, 1. And these go on forever in both directions. These are periodic functions, cyclical functions. They keep going and going and going, okay? As you can tell by the domain, from negative infinity to positive infinity. Now, the highest output is 1, and the lowest output is -1. So that's the range right here, okay? All right, so that's your cosine graph. It looks just like the sine graph. The only difference is it's been shifted over. So this high point right here has been transformed over, or translated over back to the y-axis. Okay, now, again, if you want to do the inverse of this function, the inverse cosine function is going to look, or the inverse cosine graph is going to look like this. We can also call that arc cosine. So again, look at what I'm getting. I'm not getting a function. It doesn't pass the vertical line test. So once again, we're going to restrict our domain in this original function, which basically then becomes my range in the inverse function. So instead of going from, positive infinity to negative infinity, we're restricting it from, this one goes from pi down to 0. I'll go ahead and I'll highlight it. Again, that's your principal branch, okay? So we restrict the range, which is actually the domain in the original function. And then the range of the original function now becomes the domain of our inverse function. So you'll see that this is going to go from +1 on the x-axis to -1 on the x-axis. So going back to this problem right here, can any of my outputs, actually let's call it inputs right now for my inverse function, can any of my inputs on my inverse function be 3? No, the domain on the inverse function goes anywhere from -1 to +1. Or on the original function, can any of my outputs, cosine of the original function, right? Cosine of theta, which is my original function, can any of those outputs be 3? No, on the original function, the range only goes from -1 to +1. This would have to stretch all the way up to 3. And I'm not saying that there aren't times when that'll happen. There are transformations that happen that will dilate this thing. Okay, but on the original parent graph, that's not the case. So this problem right here is undefined. It's impossible. There is no angle that I can put in for cosine and get 3 out. And if you don't believe me, come back to this and try and do cosine inverse of 3. Oops, not cosine. Cosine inverse. and look what you get. You get an error, and this is a domain error because it's not in the domain or range. Okay? So for cosine, this is going to be undefined because on the original cosine graph, there are no outputs that are 3. And on the cosine inverse, there are no inputs that are 3. Okay, remember those inputs and outputs get switched. Okay, so where does that take us here? So when we're talking about the cosine inverse function, let's see, I didn't give myself a lot of room here, but I'm going to try. So I'm going to draw it over here. Okay, so this one for cosine inverse, the range then is restricted from 0 to pi. So that's going to go from 0 over here to pi. So looking at my unit circle, if I'm given the cosine of some function, so cosine of some angle, right, equals something, I know that I'm only going to be looking between 0 and pi. So for example, if I was given cosine of theta equals root 2 over 2, like we just did on that last one, my only option would be 45 degrees. Okay? Actually, I lied about that. No, that's right. Cosine of theta equals root 2 over 2, because this cosine of theta is negative, right? And I'm only allowed to go from 0 to pi. Okay. Do one more of these. So that one's undefined. Because 3 is outside of the range of the original function, and 3 is outside of the, did I say that right? Yeah, outside of the domain of the inverse function. All right, last one here. Tan inverse of 1. Okay, so the question here is, what is that going to equal, right? So I like to set it equal to theta, and then I like to switch the inputs and outputs so that I can get back to the original function. Or basically that means take the tan of both sides, just like I did up here. Okay, by doing that, I'm going to get, on this side I would get 1 equals tan theta. I'll rewrite it so it makes a little more sense. Tan theta equals 1. So the question is, where does tan of theta, tan of what angle, will give me 1? And what you're looking for here is, because tangent, let's not forget, tan of any angle is equal to sine of that angle over cosine of that angle. Or basically your vertical coordinate over your horizontal, your y over your x. So thinking about your unit circle, if I wasn't doing this with a calculator, where would I get x and y coordinates that would equal 1? Well, again, at 45 degrees, if I put root 2 over 2 over root 2 over 2, or I did that backwards, but whatever, it's the same thing. If I put this y over this x, I'm going to get 1. Here I'd get negative 1. Down here, I'd also get 1. So the question is, which is the correct one? Well, the correct one happens to be up here, and I'll tell you why in a minute. Okay, so it's actually, your answer to this one's going to be 45 degrees. Or pi over 4 again. And you could know this just by using your calculator. So once again, you could go tan inverse of 1 is 45. Oops, sorry. But what if you weren't allowed a calculator? And guess what? Next year, you won't be allowed a calculator for most of these. Okay, so what if you're not allowed a calculator? Well, that goes back to the original function. So we'll look at that, and then its inverse. Okay, so tangent, this is the tangent function. Notice there are asymptotes along this tangent function. That's because there are places where the denominator, the cosine, is 0, and the numerator, the sine, is 1. So think about that on your unit circle, right? So for example, there would be an asymptote here at 90 degrees because it would be 1 over 0. Well, that's undefined, so we have an asymptote. Okay, and we'll talk more about that next year. Okay, so your domain here then goes, well, basically it's that it can't equal pi over 2, or that 90 degrees, plus a rotation of pi. So, plus a rotation of 90 degrees. So it can't equal this one, right? It can't equal 90 degrees, or pi over 2. And then it also can't be down here, right? Because that would be negative 1 divided by 0. So that's plus any half rotation or any 180 degree addition to it. Okay, so that's your domain. And then your range, otherwise it just keeps going, right? But except for those little 90 degrees plus 180s. Okay, and then the range here, right? These things go down forever and up forever. Okay, so what does that mean for my inverse? Well, here's my inverse function. And your principal branch is restricted. So notice the range on your principal branch goes from negative pi over 2 to pi over 2. So it's a lot like this one. Okay, it's exactly like this one actually. Okay, it goes from negative pi over 2 up to pi over 2. Okay, so let's go ahead and and your domain now is all possible inputs. Right, so your domain can go from negative infinity to positive infinity. Your range is restricted. So I know that for this one, it's also going to have, like on the unit circle, you can just go between these two quadrants. So from negative pi over 2 to pi over 2. Which, when I was doing this problem, and I said to myself, how do I know if it's 45 degrees? Or if it's 135 degrees? Nope, I lied, sorry. I didn't say 135. I said, how do I know if it's 45 degrees? Which was going to give me a positive 1, because this over this will give me positive 1. Or what about 225 degrees? Right? Where a negative root 2 over 2 divided by a negative root 2 over 2 will equal also a positive 1. Well, the tan inverse function is restricted between negative pi over 2 and positive pi over 2. So it could only be in quadrant 1 or quadrant 4. So that's why I knew that it was here. All right, let's do another example. We're going to find the measure of theta, both radians and degrees. So I'm going to give you a right triangle. And this will be the angle, my theta. This will be the opposite is 7 and the hypotenuse is 12. Okay, so I'm given a right triangle, so I can use any of my right triangle ratios, my trig ratios, to set this up. So I can say the sine of this angle, right, because I'm given opposite and hypotenuse, so the sine of this angle is the same as 7 over 12, right? That's going to be opposite over hypotenuse. Now let's solve. Now this 7/12 is not something that I'm familiar with from my unit circle. So now let me go ahead and solve for theta by doing the inverse of both sides. So basically I take both sides and I say, oh, I'm going to sine inverse or arc sine, and we'll talk more about arc sine next year. We're going to sine inverse both sides so we can undo this. So I get theta equals sine inverse of 7 over 12. So if I do sine inverse of 7/12 I'm going to get 35.685 degrees. So theta is approximately 35.685 degrees. That's in degrees. And then I can do this two ways to get it into radians. I can change the mode on my calculator, put it into radians, and then recalculate it. Or, just as a nice little review, I can take this and I can multiply it. So I can take not if I don't write it correctly. Actually, let me go over here. I can take 35.685 degrees, and I can multiply that. Well, I know that for every 2 pi radians, there's 360 degrees. Or for every pi radians, it's 180. Either way, however you want to do it. So, I like to personally reduce it. So I'm going to do this number times pi, and then I'm going to divide that by 180. And so I also know that theta can be 0.623 radians. You don't have to put anything after the number if it's in radians. That's how we know it's in radians, because it doesn't have a degree symbol. Okay, moving on to example 3, we are going to solve for all of these. We're going to do a couple of these. And we're going to give restricted domains. So solve for when cosine of some angle is equal to -2/3. And the domain's going to be given in degrees, so I know that my answer needs to be in degrees as well. So I want it some angle between 180 degrees and 270 degrees. Okay, so let's think about this. So between, out of lead. Let me switch pencils real quick. Okay. So if I think about this in a picture, I want an angle somewhere between 180 degrees and 270. So I'm somewhere in here. However, remember when we were talking about, let me find what we were talking about here. When we were talking about different angles, well, first of all, let's talk about cosine here. Can cosine of an angle equal -2/3? In fact, it can, because cosine of any angle, the output could be down to -1, right? So -2/3 definitely could be an output. Okay. Now, when we talked about, because what we're going to do right now is we're going to solve this, and we're going to use the inverse function. Okay. So why don't I go ahead and I'll do that first. Okay. So the first thing we're going to do is we're going to solve for theta. So the way that I do that is I do the cosine inverse on both sides. So I'll go ahead and I'll show that. Cosine inverse and cosine, those basically undo each other. You're just left with theta equals cosine inverse of -2/3. Okay, so let's go ahead and let's figure this out. Cosine inverse of -2 divided by 3. So I'm getting 131.810. So theta is approximately 131.81 degrees. Well, 131.81 degrees is not in this third quadrant, right? It's less than 180 degrees. So I'm actually, what I have just found right now, I just found this angle right here. Oops. That's 131.81 degrees. But it's a reference angle, okay? So the reason that it gave me that 131.81 degrees is because, if you remember, with cosine, right, I'm only allowed, as far as the range in that inverse function, I'm only allowed to go from 0 to pi. So any answer it's going to give me is going to either be in the first or the second quadrant. Okay, so what I need to do now is I need to find my reference angle. Okay, so that's what I'm going to do right now. I'm going to find this little reference angle right here. And that's going to help me finish solving this, okay? So I'm going to make a better graph. So the second thing I always want you to do is I always want you to graph the angle. I promise this is going to help you. Okay, so I graphed that angle. This angle right here, like I was just showing you above, it's 131.81 degrees. Okay, so now the next thing I'm going to do is I'm going to find the reference angle. Okay, so I'm going to look for this angle right here. And that angle, whatever it is, so let me tell you what it is. It's 180 minus 131.81 is 48.19 degrees. So this right here is 41.89 degrees. And I'm supposed to be between 180 degrees and 270 degrees. So the next thing I can do is say, well, if this is the reference angle, well, and I want to be in the third quadrant, then I can add that reference angle to the third quadrant. So this angle right here is also 41.89 degrees. And so I know that the angle that I'm actually trying to look for, which is, I'll highlight it, the angle I'm actually trying to look for is this angle right here. Well, that angle is just going to be 180 degrees plus 41.89 degrees. So next step here is to find my angle. And the picture is what's going to help you find the angle. I can't say, oh, it's always going to be 180 plus this. Well, there will be little formulas that we'll learn next year, but we're going to save those for next year. So to find this angle, I'm basically going to say to myself, I'm going to take 180 degrees, and to that, I'm going to add 41.89 degrees. Leaving me with a total, I guess I should say it's approximately, because none of these are actually, because I did round, 228.19 degrees. Okay, let's try that again. So let's do the same thing. Actually, this one will probably be way easier. So we're going to do the same directions, and we're going to solve sine of theta equals negative 1/2. So right away you should say to your, and where theta is in between 3 pi over 2 and 2 pi. Excuse me. Okay, so what does that actually look like? Well, 3 pi over 2 is here, and this is 2 pi. So I know that I want an angle somewhere in here. Now, this should look very familiar to you. There are outputs on the unit circle that are negative 1/2 for sine. So there are outputs that are 1/2, still 1/2, negative 1/2, negative 1/2. So it's one of these two. And I know that I want to be, basically, it tells me which quadrant to even be looking for between 3 pi. I know I want to be here. So it must be this example where sine of this angle is negative 1/2. And sine of this angle, well, the angle is 11 pi over 6. The sine of it is negative 1/2. So your theta that you're actually looking for is 11 pi over 6. So that's kind of a quick and easy way. So you had two options to choose from, right? There was this option here where sine was negative 1/2. Or there was this option here. These were both negative. Where sine was negative 1/2. And you would want to choose this angle here because it's in the right quadrant. And that angle happened to have been 11 pi over 6. And I'll just say right here that I used my unit circle. So that's another way that you could have gone. However, let's say that we wanted to do it like we did above. Okay, so this is one way. Another way that I could have gone is I could have said, well, theta will be the exact same thing as sine inverse of -1/2. Go on to my calculator, or hopefully you know your unit circle and you know that that's going to be a 30 degree. So that's a -30 degrees. Okay. That basically, by the time you draw that picture, you're going to say to yourself, this time I am in the right quadrant, right? That's the quadrant that I wanted. Okay, and -30 degrees. Oh, I was in degrees, but it's better to be in degrees anyways because the radians wouldn't make any sense. You'll end up with a decimal. So I'm -30 degrees. That's a pi over 6. A full rotation would be 2 pi, right? Subtract a pi over 6 from that, and you're at 11 pi over 6. So this angle right here would be 11 pi over 6, which I got just by using the unit circle in the previous example. You don't have to add anything. You don't have to subtract anything. That's why it's so important that you draw these out. Because like back here, I couldn't say every single time you're going to do it this way for every single trig function. Can't say that. Okay? And I can't say that, you know, this format's going to follow this format. Now, next year, I'll give you a little bit of a formula because they're different for sine and cosine. Okay, let's see. What else do I have? I've got one more example for you. All right, unfortunately, we got to write it out. We got a crane, not a bird, like an actual construction, heavy equipment crane, whose lower end is 4 feet off the ground. Hold on, I'm trying to read it. A crane whose lower end is 4 feet off the ground, has a 100-foot arm. The arm must reach the top of a building. That's 80 feet high. At what angle should the arm be set? I'm going to draw myself a picture to help me out with this. So I've got some crane here. Let's just pretend like that's a beautiful picture of a crane. It's on some kind of wheels. I don't know if it's got like the tractor wheels or if it's got like the bulldozer wheels. I'm not 100% sure. And so the crane itself, this part right here, is 4 feet off the ground. It's got an arm that's reaching up, and that arm is 100 feet. Oops, the arm is probably at the base of the crane, not at the top. Basically, yeah, because it's 4 feet off the ground, that arm is coming up from after being 4 feet off the ground. And then we have some building that we need to reach the top of, and that building is a total of 80 feet. This crane arm is 100 feet. Don't do these without drawing a picture. It's too complicated to try and figure that all out. Okay, so Notice I can draw this basin right here and have a right triangle. And because this building is 80 feet, but my crane arm is actually 4 feet off the ground, then this side right here would just be 76 feet. The question is, what is the angle that the arm should be set? So what angle should the arm be set? Okay, so that's what we're looking for, is that theta. So notice in relation to this theta, I have the opposite and I have the hypotenuse. So I'll go ahead and I'll use sine. Sine of what angle will equal 76 over 100. To solve for theta, I'm going to do sine inverse on both sides. Notice that, my output here is less than the absolute value of 1, which is good because the outputs should either be positive 1 or negative 1 or somewhere in between. Okay, that's just thinking about the range of the original sine function. Now, if I'm working in construction, and hopefully you know some people that do work in construction, they're going to tell you that they're working usually with degrees. Okay, so we are going to work in degrees. So make sure that your calculator is still set for degrees. I think mine's been in degrees this whole time. Working with radians, a lot of times, you're going to end up with quite a bit of decimals unless you understand your unit circle. Okay. All right, so to get theta by itself, I'm going to go sine inverse of 76 over 100. Right? I just inverse both sides. If I do that, sine inverse of 76 divided by 100, I get 49.464. So theta is approximately 49.464 degrees. And that's it. I basically answered the question, and the answer makes total sense. If I had gotten some other answer, like a negative, then maybe I would go back and I would draw and figure out what the reference angle is and get it so that I had a positive angle. If I had another angle that didn't make sense, like maybe it was more than 90 degrees, same type of thing. However, for sine, as we had talked about, you'd probably only either get a negative angle or a positive angle, somewhere in the first or fourth quadrant. Okay, so things I haven't talked about are like the secant inverse, the cotan inverse, and the cosecant inverse. But you can basically pick those up off of the sine inverse or the cosine inverse or the tan inverse. You can use those same rules, it's just the reciprocals of them. Okay? We will definitely go into way more detail about those next year. But I think I'm going to cut this video, call it done.